Hi, my name's Dan. This video is one of a fairly large suite of videos with the ultimate aim of going from uh, the fundamental logic gates to a simulated 4-bit CPU. I'm doing this using simulation software called DigitalWorks. There is a link to that software in the description down below. There is also in the description down below a roadmap of where we're going in terms of developing this CPU. And at this point, this inside that larger suite, I've got several shorter series of videos which are going to be YouTube playlists. And at this point now, we're starting to develop a memory bank. So we've done a whole lot of stuff already about digital circuits, memory and how it works, and we've created the ability to store single 4-bit bytes in registers, and our CPU that we develop is going to need access to a memory bank. So over the next 3 videos, we're going to develop that. And in this video, um, not actually making anything and just talking through what we're going to need and how we're going to do a memory bank. And thinking about the components that we might need. So we're going to ask this question: what do we need? And come up with some answers. So fairly basically, we need a load of memory hardware. Yes, okay. And we might as well use registers because we've already created memory hardware that's uh, in the form of 4-bit registers. So we're going to reuse those to make our memory bank out of. In real digital electronics, some of the components that are involved in there would be unneeded, and so we'd pare this down and have specific components for this purpose. But for the sake of this simulation and keeping things simple, we're just going to reuse the same component as we're going to be using for registers as well. So the question is, how many? Oh, lots. We want as many as we can have. Surely that's the thing. But we've got a problem. Okay, which is, so our ultimate aim is that we're going to be working in 4 bits. And at this point, this is possibly the first time that I'm going to justify why 4 bits rather than a more normal 8-bit. 8-bit would give you much more capabilities because it's not twice the size of 4-bit. It's 16, no, yes, 16 times the size of 4-bit. Um, and so you'd be able to have 16 times the number of memory locations, you'd be able to have 16 times the number of uh, uh, operations, different commands that you can have. All sorts of things become better in 16, in 8-bit. However, in the past, using DigitalWorks, I have attempted to make an 8-bit memory bank like I am doing here with a 4-bit one, and the slowdown was considerable because it just couldn't cope with that many gates running at once in a simulation. So this is why we're doing 4-bit, is because somewhat for the needs of the simulator, somewhat for the sake of complexity as well. So it makes things, in some ways, simpler. Anyway, that's my justification. So we need to access the registers that we've got, and as I've kind of indicated, we're working 4-bit, so we've only got 4-bit addresses. So we're actually only able to have a maximum of 16 memory locations in a memory bank. We might have more than one memory bank, and we'll deal with that later on as a way of expanding the capabilities. But for now, in one bank, we're only going to be able to have 16 addresses, and so that means we need 16 registers. Okay, what else do we need? Well, we need the memory bank to be able to communicate with the outside world, with other components inside our simulated CPU. And I'm going to use a general principle for this project. This isn't a general principle that is particularly applicable across digital electronics. So it's just for the duration of this project. I'm going to say that when we have a component that has any form of output, that if it seems reasonable, and it probably will most of the time seem reasonable, that we're going to use an internal bus-ready register in the component to do that output. So in terms of communication with other components, we're going to need to build into our memory bank an I/O data register. So this is an extra register, a 17th register, which we're going to use. I/O stands for input output. So when we're reading from the memory, that will extract the we'll extract the data from the specific address and put it in the I/O data register, and then that can be used on the on a bus that's widely available to all the components in our CPU. And similarly, when we're wanting to write to the memory, we will take this. We will take whatever the data is to be written, and we'll put it in the I/O data register, and then from there we will write it into the specific location in memory that we're going to use. Um, we also need internal communication. So once we've got more than one component in there, things are going to need to talk to each other. And we've kind of indicated in the past that buses are a good way of doing this. So we're going to use an internal bus inside our memory bank. Okay. This actually implies something quite interesting about that I/O register that we talked about, which is that it needs to be able to communicate with the internal bus and with an external bus. And so it's going to be a special kind of register in that it's going to be a dual bus register, and it's going to have the ability to talk to an internal bus and an external bus. And in fact, we will create a dual bus register, which we will just call them bus A and bus B in that, and it'll have separate lines to connect to the different buses and separate bus read pins and output enable pins for the two different buses. And in the next video after this one, we'll spend some time creating that dual bus register. Um, anyway, so internal communication, internal bus. We also want to be able to specify which memory slot we use for at any particular point in time, and I've implied that as I've been talking through what we're doing. So we're going to need memory addressing, and that's going to be a 4-bit binary number. Okay, let's go back to general principles for this project. So we had a general principle that if we had an output from a component, that we were going to build a register into that component to be used for output, which is going to then communicate with a bus. Um, uh, as a kind of mirroring of that, I'm going to make input for components data pins and not a register. And so the question is, why not? Why am I not putting a register on the input and a register on the output? And the answer is because sometimes the input for one component is the output from another component, and you want the two components to connect together. And that means that that output is already a register. And so rather than multiplying up the number of registers that we're going to have by having an input and an output register in each component, I'm going to have this principle that if there's a component that has a register then built into it, then that register is conceptually the output. In the case of the memory bank, it's an I/O, but in the case of the address, that's only ever used as an input. So we're going to use, for memory addressing, we're going to use a memory address input, and it's just going to be 4 pins for that. There will be externally in the rest of the hardware a register which will connect to that, which is called the memory address register. But let's not worry about that for now in terms of building the memory bank. We're also going to need some form of controls. What do we need controls to do in memory? Well, it's fairly straightforward. We need to read, and we need to be able to write. So the external hardware to this is going to want to be able to access the individual memory locations as we've got. And sometimes it's going to want to write to the memory bank, and sometimes it's going to want to read from the memory bank. And so we need to write to whatever specific address we've got being input, or read from the specific address that's being input. And we have got this kind of intermediate phase that we're going to use, which is we're going to use the I/O register as an intermediary in that process, but we still do need to have these controls to be able to go in. So we've got a 4-bit number coming in we're going to want to route that 4-bit number to one of 16 registers with the control that's coming in. And this quite clearly tells me that we need to use binary decoders for this. So we're going to have a binary decoder for read and a binary decoder for write. It might have been possible to save some hardware here, but once again, for the sake of clarity, we're just going to use two separate binary decoders for this. Okay, we're nearly there. And finally, we're going to want the ability to clear the whole bank just to kind of do effectively a reset and set everything to 0. That won't need an address because it's going to work across the whole of the memory bank. So it will not need a binary decoder in order to do that. I think that's just about everything. And I know where we're going because I've done this before. Hopefully you can kind of think through that this might be the things that we need. You might not understand how all this fits together yet, and that's fine. That's what we're doing in this short series of 3 videos. But we're going to look at this. This is our shopping list of our capabilities, and I'm going to quickly look through in terms of hardware. What do we have and what do we need? So 16 registers, we already have bus-ready registers. An I/O dual bus data register, that is something we don't have. We don't have a dual bus register. An internal bus, that's just wires. Memory address input, again, that's just wires. Read-write with binary decoders, we've got 4-bit binary decoders, so we can do that. And we've got the ability to clear the whole bank. That's just one wire connected to all the registers. So we should be fine. So the only extra hardware that we don't have already is a dual bus data register. And in the next video, we're going to develop that, but that's it from me for now.